Hello everyone, welcome to this course. In this course, we are going to delve into the interesting world of hydrogen and its derivatives. So, welcome again. My name is Pratham Arora and I am an assistant professor in the Department of Hydro and Renewable Energy, IIT Roorkee. I, along with my colleague Professor Amit Bhosle, are going to take you through this course which basically dwells into the economic as well as the electrochemical aspects of hydrogen energy. As all of you are aware that hydrogen holds a lot of promise in the ongoing energy transition. If you read the popular literature, the newspapers, the TV channels, all are filled with the interesting news that keep on happening in the sphere of hydrogen energy. So this course is basically meant to equip you to understand how does hydrogen economy is expected to work, and further what could be the intricacies that are linked to the use of electrolyzers and fuel cells, which basically depend upon electrochemical technology. Going further, in the start of the course, we'll try to make you understand about the energy scenario in general and why hydrogen is expected to play a major role. Then we try to understand what are the current market for hydrogen, what could be the possible ways of production of hydrogen. Then we delve into the deep secrets of electrochemical hydrogen production as well as utilization. And what do you do once the hydrogen is produced? How do you store it? How do you transport it? How do you use it? Then follows. Finally, we'll try to understand the economics that works behind it and the emissions for which the things are going on. For this lecture, currently, we'll try to understand, do we really need an alternate for energy use? We seem to be living a happy life. Or why do we need to shift towards an alternate in the form of hydrogen? So in today's case, we'll take a simplistic example. We'll do some calculations together and try to estimate that what if we go by the business as usual, the energy consumption goes on as usual, we keep on using the fossil fuels. That also entails there would be somewhat of a CO2 emissions, and if the CO2 emissions were to continue, what could be the likely problems or the likely challenges? So what we will do or try to do is try to understand if all of the energy that we are using today and in the coming few years was to come from fossil fuels, majority of energy as such is coming from fossil fuels for today, what could be likely CO2 emissions, and in that scenario what would be the time that would be required for doubling the CO2 emissions globally. So if I write the objectives of today's lecture, this could be as to understand the use of energy by humans, and the second thing we will try to understand is to estimate its likely impact. The impact that is going to come from the use of the fossil fuels. So first let us try to have a view of the night sky. So I found this interesting picture which was assembled together by NASA, which basically shows you the night sky, basically clubbing in a lot of pictures together, and it also shows you the transition that has happened between the years 2012 and 2016. Where are the places where majority of the lights have come up, and there are a few places where lights have dimmed as well. So basically what you see on the orange is the lights going off in certain places, and what you see in the purple color is basically the new lights have come up. So one thing that we see in here, that the earth as a whole has a huge energy consumption, but this energy consumption, which basically can be seen with the help of the spread of these lights, is not equally distributed. There are places on earth, basically if you see the parts of Africa, South America, or the north of Asia as well as the Americas, they are not having hardly any lights, possibly because most of these places are not habitable by humans, and there is also a problem like not many people in these places might have access to electricity and other energy needs. As such, if we see, the energy use globally is not equally distributed, but it's quite spread out and quite distinct in different parts of the world. But for this calculation, let us consider the globe to be one family and which are consuming significant energy. So if I talk about the total energy consumption globally, we arrive at a number which is possibly of the order of 600 exajoules. So when I use a term called exajoule, this basically refers to 600 into 10 to power 18 joules. Joules, I believe all of us understand, is a unit of energy, and as a family, as a globe, the human race have been using roughly 600 into 10 to power 18 joules every single year. Of course, there would be fluctuation in this number. If you see the number currently for the year 2025, it could be roughly 620 or something. But like for the sake of this calculation, let us assume that this is the energy use that is made up by humans. Now, when we are using this energy is nonetheless coming from fossil fuels. Majority of the energy, as we will see in the later part of this class, is coming from fossil fuels. And when we are using fossil fuels, a likely impact or a likely product is the production of carbon. So what we are going to do in this small exercise that follows is we will try to estimate if whole of this energy was to come from fossil fuels and the likely product is CO2, what will be the time that will be taken to double the amount of CO2 that we have in the atmosphere. Doubling the amount of any gas in the atmosphere has serious consequences. This is what a majority of major scientific publications also refer as a target to understand the likely impact of CO2. So we are going to do the simplistic calculation and see the number for ourselves. So before we begin, we need to understand the major constituents of atmosphere. So if I was to write the major constituents of dry air, and here I am talking about the volume percentage. Most of us have studied in our school days or engineering days that majority of the atmosphere is occupied by a gas called nitrogen. It's basically more of an inert gas, not much of a problem, and the percentage on a volume basis is roughly 78.084%. Then comes in oxygen, which is vital for our survival, and oxygen makes up roughly 20.946% on a volume basis of the atmosphere. Then comes another gas, argon, which is a noble gas, roughly contributing to 1%, and the exact concentration would be 0.934%. Then comes in a gas which many of us are concerned about, and it is called carbon dioxide. The concentration of this gas on a volume basis in the Earth's atmosphere is very small. It's roughly 0.040% or 400 ppm as it is generally told. So on an absolute scale, you might think that it's hardly any gas that you should be worried about. But that's not the case, because if you read the popular literature, if you read the news, climate change is a big issue. Every policy that we now derive is basically focused or taking into account the climate change that is going to come up in a big way. And the small percentage of this gas, an increase in that could have serious consequences. And this is what we'll try to understand from our calculations. So this is the gas composition that we have in the atmosphere. CO2, which is a gas of concern, although less, but it is an important gas. Further, there could be another component of this atmosphere which comes in the form of water vapor, but as of now in this study we are just considering dry air. The water vapor or the moisture content could vary from 0 to 5% depending upon which place you are residing in. But for the sake of simplicity, we are going to take that assumption that there is no water content in the atmosphere. And the second thing we need to understand is the different layers of atmosphere, which you can see in the slides in front of you. So the atmosphere as such is formed of different spheres, each stacked one upon the other. The layer of the atmosphere which we have starting from the sea level going up to the almost 12 kilometers of height is known as troposphere. Troposphere is a sphere where we can expect majority of the economic activities to happen. This is also the place where majority of us are going to spend their entire lives. If you talk about the highest peak, Mount Everest, roughly at a height of 8,500 meters. If you talk about flights, long distance intercontinental flights, they fly at a height of again 10 kilometers or so. So most of us are going to stay in this atmosphere for our entire lives. which is called the troposphere. Beyond the troposphere, we have the layer called the stratosphere. This extends from 12 kilometers to 50 kilometers of height. This is also the place where you have the ozone layer. This is also the place where you have the weather balloons, which are used for weather prediction, flying. Beyond the stratosphere, you would have the mesosphere. So in case you're lucky enough to see some meteor showers in the night, this is the layer in which you can see the meteors. Above the 90 kilometers of height, we have a layer called the thermosphere, where you would possibly find the International Space Station roaming around at around 400 kilometers of height, and some satellites as well. Those of you might have seen the northern lights in places like Ladakh or some of the Nordic countries. This is the layer in which you have the aurora formation that is happening, and beyond the thermosphere, going till the reaching to the external space, is something called as exosphere, which extends to almost 3000 kilometers or so. As such, if I talk about the human race, most of us are going to spend their lives in troposphere, and troposphere is also the place where almost 80% of the weight of atmosphere is concentrated. So let me repeat again, 80% of the weight of the atmosphere could be found in just one layer, which is called as troposphere. So for the sake of simplicity, we'll try to consider that whole of the atmosphere can be replicated by atmosphere. The reason we are doing that is because 80% of the weight of the atmosphere is concentrated in the troposphere, and further, this is the sphere which is of economic importance to us. Now, going to the second aspect of this calculation, where we try to understand the production of energy, likely side products of this energy production. Now, after the consideration of the whole atmosphere being replicated by the troposphere, the calculation would be trying to estimate the volume of this troposphere. We all understand that the radius of Earth is around 6371 kilometer along, and also Earth is not a complete sphere. It is basically more pressed on the poles, but for the sake of simplicity in this calculation, we will assume that Earth can be represented by a complete sphere with having a radius of roughly 6371 kilometers, and above this would be the troposphere, which spans for 12 kilometers of height. If I have to calculate the volume of Earth, we can use the simple formula, which is 4 by 3 pi r cube, and this will give us an answer of roughly 1.083 into 10 to power 21 meter cube. I would encourage all of you to do this calculation along with me, so that you know that how these numbers are coming from. Now further, using the same methodology, I can also calculate the volume of Earth plus the troposphere, which I believe would represent whole of the atmosphere, and this would be nothing but 4 by 3 pi, and in this case I am going to take 6371 plus 12 and a cube of the whole. The value of this particular number you can calculate for your own self, and then subtract the two spheres to get the volume of the troposphere, and the volume of troposphere would come out to be roughly 6.132 into 10 to power 18 meter cube. So what I did just recently was I calculated the volume of Earth, I calculated the volume of Earth plus troposphere, subtracted the two, and this gave me the volume of the annulus, which is represented by troposphere and atmosphere as a whole, and this is the volume of the troposphere that is of concern. Now second thing that I would want to do is calculate the amount of CO2 in this troposphere. So if you remember, CO2 in this troposphere was roughly 0.04%. So if I multiply this number with 0.04 and divide by 100, this is going to likely give me the amount of CO2 that is going to be there. So the amount of CO2 I can calculate would be roughly going to come out to be 2.453 into 10 to power 15 meter cube. I calculated the volume of the troposphere. Next, I multiplied this with 400 ppm or 0.04%, and this gives me the current volume of CO2 that is there in the atmosphere. Now, this is there the volume or the amount of CO2 that is already there, but I am also continuously emitting CO2 by the use of fossil fuels. Now, if these fossil fuels are getting used, the CO2 is getting added up, and I would want to understand what will the time required for an additional amount of CO2 which is exactly the same amount. This means I am doubling the amount of CO2 in the atmosphere. So now let us try to do that calculation. So for this calculation, let us try to understand the composition of fossil fuel, and I will take a fossil fuel which is widely used in the form of crude. So let us start with the composition of crude that is available. And this composition I am writing on a weight basis. So the crude basically, or any fossil fuel, is majorly deriving its energy from the carbon content. So if I talk about the element that is majorly present in fossil fuels, it's the carbon. And if I talk about the weight percentage of carbon in crude oil, this would be roughly 83 to 85%. Next comes another element, hydrogen, which is going to be the basis of this whole course, roughly 10 to 14%. Nitrogen again 0.1 to 2%. Oxygen 0.05 to 1.5%. Sulfur 0.05 to 6%, and few trace metals normally of the order of less than 0.1% or so. So this is the normal composition of crude that would be used for meeting the different energy demands. And as we can see, energy from crude is basically coming from two elements, which is carbon and hydrogen. Again, for the sake of simplicity, I am going to assume that majority of or all of the energy from the crude is going to coming from carbon, which is the case as well. I am going to neglect the energy that is going to come from hydrogen. So I am again making a simple assumption wherein I am assuming that the energy for the use of crude is going to come entirely from carbon. So whenever I am using carbon, the equation remains simple, that carbon is going to react with O2 and produce a molecule called CO2. And this is an exothermic reaction which is going to produce energy. And the amount of this energy that is going to come up by the simple reaction is minus 394 kilojoules per mole of CO2. So let me repeat it again. When I am using fossil fuels, it's essentially I am using the carbon content of those fossil fuels, reacting this with oxygen and producing the one molecule of CO2. Now this is an exothermic reaction which will produce energy, and for 1 mole of CO2 that is produced, normally I would be emitting 394 kilojoules of energy. As such, the reaction is very complex, involving a lot of radicals and other side reactions, but this is for the sake of simplicity, I am assuming that this is an overall reaction that is occurring, and for the production of CO2, this is the amount of energy that is released. Further, we have understood in the earlier studies that you would have done that we can convert moles into volume. So normally at STP, which is 0 degrees Celsius and 1 bar pressure, 1 atm pressure, 1 mole of a gas is equal to 22.4 liters of that gas. But this relationship is applicable only till STP. But if we consider the Earth's atmosphere, I'll go back to the slides. You can also have a look at the temperature ranges. So as we proceed or rise up in height, the temperature is going to reduce. As in the case of the troposphere, which is the sphere of concern in our case, the temperature goes as low as minus 56 degrees Celsius. That starts from nearly room temperature and then reduces as we increase the height. And if I have to consider STP to be applicable to the whole of a troposphere, I might not be doing much of an exaggeration. and this is what I will be assuming, I will consider that whole of the troposphere is essentially present at STP, which is 0 degree Celsius and atmospheric pressure, which is the case. So, if this is the case, I can assume that 1 mole of CO2 is equal to 22.4 into 10 to power minus 3 meter cube of CO2 that is present in the troposphere. Now, the next part of this calculation is, if now all of the 600 exajoules, which is the primary energy consumption that I have on the planet Earth, was to come from this fossil fuel, and I am estimating all of the fossil fuels to be represented by this crude, what is the amount of CO2 that I would be emitting? So, the CO2 released by energy use would be the energy consumption, which is 600 exajoules or 6 into 10 to power 20 joules. I divide that with the energy release from 1 mole of CO2 production from the combustion of carbon. This is 3.94 into 10 to power 5 joules per mole. And now I need to convert this moles into meter cube. So, I multiply this with a factor of 22.4 into 10 to power minus 3 meter cube per mole. So, we will have joules, joules cancel out, moles and moles cancel out, and what I get is the production of CO2 in meter cube, and this would come out to be 3.411 into 10 to power 13 meter cubes of CO2 getting produced per year. So, this is the amount of CO2 that I would be producing per year if whole of the energy on the planet Earth is going to come from the use of fossil fuels, and these fossil fuels are basically being represented by crude. Now, I have two numbers. One is the amount of CO2 that is already there in the atmosphere, and the second is the amount of CO2 that I am continuously emitting because of my energy use. I divide the two and I get the number of years that would be required to double this amount of CO2. So, let us do that. So, let me write the time required to double this CO2. So, this would be nothing but the CO2 that I already have in the atmosphere, which came out to be 2.453 into 10 to power 15 meter cube, divided by the production or the yearly production, which is 3.411 into 10 to power 13 meter cube per year. And if you do this division, you will get the number of years that would be required to double this amount of CO2, and this would come out to be roughly 72 years. Now, it depends whether you think this 72 years is a big amount of time or a small amount of time, but if we study seriously, we will see that this 72 years might not be a very great amount of time. It could basically be reached in 3 generations. So, within a span of 3 generations, the CO2 content in the atmosphere can almost double. Again, this is not a very in-depth calculation, but a very preliminary calculation where I have made many assumptions. Again, I would like to list the assumptions. I have considered the Earth to be a perfect sphere, which it is not. I am replicating whole of the atmosphere to be equivalent to troposphere. Again, that is not the case. I am considering whole of the energy to come from fossil fuels, and even among the fossil fuels from crude, and even in the crude the energy is going to come only from carbon, which again might be a bit of an exaggeration. Another problem that with this calculation is I am assuming the energy consumption of the planet Earth to be constant for the coming few years, which again is not going to be the case. If we see the past, the energy consumption globally has continuously been rising. If this number was to be rising in the future as well, possibly the answer for doubling the amount of CO2 will even be lesser. Suppose we double the amount of energy consumption in the next 10 years or 15 years, possibly if I have to double the CO2 in that case, it will come out to be roughly 36 years. If I increase the energy consumption to a greater extent, this number can be even lesser, maybe even 1 generation. So, again, this is not a complete calculation, this is not a perfect calculation, but this is just to give you an idea that the problem at hand, and this is the problem with the fossil fuels in general. If I am using fossil fuels in the form of coal, natural gas, crude, inherently the energy is coming from the carbon content. It might be great, a large amount of carbon content as in the case of coal, or it could be slightly less as in the case of natural gas, but the likely product or the main product is going to be the CO2, and this CO2 is going to be coupled with the energy production, and this is one of the reasons why we need to move towards an alternate economy where CO2 is not the main product of any fuel that we use. And that is why we are searching for alternate economies. Some people suggest hydrogen economy, there are few others who would suggest methanol economy, ammonia economy, and few other molecules. But all of them have to do with hydrogen and its derivatives. And this is one of the reasons why globally all the leading countries are now finding a way to move towards one aspect of hydrogen economy or the other, because they want to do away with this side product of this carbon combustion, which is causing a major trouble. Further, we also need to understand, of course this is good for calculation sake, but do we have any validation of this as well? Have we experienced some things in the past which justify this calculation of ours? So let us try to have a look at the past CO2 profiles that we would have on the planet Earth. So here is some data for the CO2 concentration in the atmosphere for the past 1000 years or so. The data that you can see marked in the magenta color is basically coming from the CO2 concentration that was measured from the gas that was captured in the polar ice caps, and a measurement was done. The one in the blue are basically the direct measurement that are happening in an observatory in Mauna Loa, Hawaii, where they are directly measuring the CO2 concentration. And if we see the CO2 concentration profile for the past 200 and 300 years, we see that the CO2 concentration was almost stagnant at around 280 ppm. But something happened in the year 1769 and there was a drastic increase of CO2 since then. Most of you would have guessed it right. What happened in 1769? It was the influx of the Industrial Revolution, which was basically initiated by the discovery of the modern steam engine by James Watt. So this is precisely the year when the steam engine by James Watt was discovered, and beyond that we see there has been a steady rise in the CO2. What is interesting to note here is, along with this rise in CO2 is also a coupled rise with the global use in the fossil fuels. We see it was basically propelled by the use of coal in the UK, because that was the epicenter of the Industrial Revolution. Further, the world coal production picked up, and then we had the oil use picking up in the US and the Middle East, and closely coupled what we see is the CO2 rise. So if we see the reality, we see that things have been happening quite in a validating way, that the global energy rise is nicely coupled with the CO2 rise, as we have seen in the past. Further, we also need to understand that the CO2 levels on the planet Earth have not been stagnant for a long time. There always have been fluctuations because of the precision of Earth and because of the movement of Earth and the Sun. But if you see the past millions of years, this is how the change has been. The current fluctuations in the CO2 is majorly attributed to the global rise in the use of energy, which is primarily coming from fossil fuels. Again, we have seasonal variations which are basically dictated by the growth of plants and other natural phenomena, but these fluctuations are again on a rising trend. So globally there is now a consensus that majority of this CO2 emissions are linked to the energy use. So if we would have to put a curve on the problem of climate change that we all face, we would have to do something with respect to this carbon emissions that are closely linked to the energy consumption. Further, how does CO2 affect us? It affects us with the leading to rise in the temperature or global warming, as it is called. The Earth's temperature has been steadily rising for the past 150 years or so, and if it was to further rise in the coming few years, it could have serious repercussions which could have economic effects, social effect, governance effect, and environmental effects. And also, if we have a look at the final energy consumption till a few years back, we would see that majorly our energy is coming from three sources, which is coal, oil, natural gas, and a majority of electricity is again being produced from this coal. So more than 80% of the energy that normal people like you and me consume is coming from these three fossil fuels. And it's also interesting to note that this energy consumption has always been increasing in the past. Of course, there were a few hiccups in the past, like you can see the economic upheaval of 2008 making a kink here, and if you see the future data, you would have a similar kink for the COVID years as well. But as such, the energy consumption has always been rising, and this is something we need to be concerned about. We need to understand if we consider or if we keep on going with the business as usual, there could be heavily CO2 emissions which could have not so great effects for the future of the planet. And again, we also need to understand there are certain regions of the earth which are going to propel the energy use in the future. If you bifurcate the energy use and its increase, you will see that most of the OECD, which is a developed world, has almost stagnated in the terms of energy consumption. Where do you see a majority of energy rise happening? It's basically China and other parts of Asia, of which India forms a major proportion. So we can see a great influx of energy increase happening in India, and it is up to us to decide how this energy is going to come up. And this is why the role of hydrogen economy becomes even more pertinent. So with this, we would like to take a break for the current lecture. So from this lecture, we conclude that the energy use by humans could have significant consequences, and these significant consequences by the use of these fossil fuels can come up in a fairly short amount of time. And I also like to attribute Professor Pratap Haridas from IIT Madras, from whom I have learned this calculation and sharing with all of you. With this, I would like to take a break for the current class. Thank you.